All right, we're moving on again. This is part three now of the May June 2020 series, 9701, paper 1-1. All right, let's just keep going. I think we're doing 22 through 30 today. But let's just double check. Yep, 22. All right, let's just move on from here. Okay, so it says butylenene and butadiene are treated separately with cold dilute acidified manganate 7 ions. Okay, so if you treat it with cold dilute acidified permanganate, basically it's just going to perform a double alcohol thing, so it's a diol. Let's see. Oh yeah, see right here, diols formed from them. Oh my god, I hate it when it does that. Okay, well, before we even read them, let's see what it actually does. So butylene, let's see, one, two, three, that is 4 carbons. Butylene looks like this. Butylene, here, let me use a different color. Butylene looks like this. That was bad. Boom, oh my god. Butylene looks like that. So what butylene will do is when it performs a double double alcohol creation, basically, it basically does this. So you have an alcohol here, and you have an alcohol here. And basically what I'm doing here is if you look at the ends, right? Wherever the ends of that double bond are, just attaching alcohol onto them on both sides. So in this case, for the other one, butylene, it'd be over here. So what this will do is it'll form an alcohol going here and here. Okay, so let's see what they want. So student W says there is a one diol that contains two primary alcohol groups. Well, a primary alcohol will be an alcohol that has one carbon group attached to it. And in this case, there is only one primary alcohol, and that is this one right here. The other ones are all secondary, so student W is incorrect. Moving on. Student X says that one diol contains a primary and a secondary alcohol group. Well, butylene, when it transforms into a vicinal diol, it does do that. There's a primary alcohol right here and a secondary alcohol right there. So student X is correct. Student Y, on the other hand, let's see. One diol contains two secondary alcohol groups. Well, if we look at the butylene, when it turns into 2,3 di, well, 2,3 butanediol, there we go. There is a secondary alcohol right there and a secondary alcohol right there. So that is correct as well. And then finally, student Z, both alkenes exhibit cis-trans isomerism. That is not the case because, well, this one right here, butylene does, because again, you have an H here and then the CH3 there, and then again, an H here, wait. You have an H here and then a CH3 there. This one has two H's on one side and then a C2H5 and then an H. So butylene does not exhibit cis-trans isomerism, only butylene does. So it's not both, it's only one. Therefore, student Z is incorrect. So they asked which two students are correct. Well, the two students would be X and Y right here. So that would be answer choice C, which I do believe is the correct answer. All right, moving on. 2-bromo-2-methylpentane. Okay, let's draw this out first. So 2-bromo-2-methylpentane looks something like this. So you first have the pentane, so 1, 2, 3, 4, like that, and then 2-methyl, and then 2-bromo, which would be like that. Okay, so you have a tertiary halogenoalkane. Okay, that's what this is, because there's, 1, 2, 3 carbon groups attached to there. All right. Which organic products are formed when the 2-bromo-2-methylpentane reacts with a hot concentrated ethanolic solution of sodium hydroxide? Okay, so what this does is it eliminates the halogenoalkane and it basically just transforms it into an alkene. So what it'll do is if we draw it out like that, we take off the bromine and we form a double bond. So the double bond has basically three options of where it can form. You can form one here, you can form one here, and you can form one here, like here. Now, the trick is you have to notice that this one right here and this one right here are the exact same molecule. And the reason for that is because if you were to rotate this carbon around on its side by a little bit, you notice that you can just flip the two positions of these two things and it would still be the exact same as this one right here. So in reality, you're only getting two actual compounds. You're getting this and this. So let's just figure out the names of these. This right here would be, let's see, 1, 2. So it would be a 2-ene. We know that. And we also know that there are 5 carbons. So 1, 2, 3, 4, 5. Because again, we started out with a pentane. So this will be pent 2-ene, we know that. And there's also a methyl on the second one right here. So it'll be 2-methyl, 2-methyl pent 2-ene, which is this right here. And then this one right here will be, let's see. First of all, you have your alkene on the 1. So it'll be a pent 1-ene. And then we also have the methyl on the 2 because we are going 1, 2, and that methyl right there is on the second one. So that will be 2, oh my god, sorry, it's a little bit cramped here, 2-methyl pent 1-ene, which is indeed that next option right there. So that would be answer choice B. And yeah, that's basically all there is to it. The only case where you'd have to really watch out for what might happen is in the case of when you can't really form a double bond. So for instance, instead, if we had a compound that looked something like, I don't know, you still have the pentane. Let's say you had something here and here, let's say, and then let's say you also had like that. Same case as before. You can no longer form a double bond here because then this carbon would have 5 bonds attached to it. But yeah, in the case that arises, just watch out for that. I just wanted to show you an example where that might come up. Anyways, let's move on to the next question. Polypropene is an addition polymer. Okay, so we have addition polymerization here. What are the carbon-carbon-carbon bond angles along its polymer chain? Okay, so first things first, whenever you find a poly whatever, the first thing you should do is draw out that said molecule. So propene looks like this. And if we were to draw out its displayed formula, it looks something like this. So CH3, H, H, H. And whenever you're drawing an addition polymer, just turn that double bond into a single bond and then attach 2 wings going out like that. So that will become CC, boom, boom, CH3, H, H, H. And basically this right here is the repeat unit. So you can write N if you want. And what it means is you basically can have the exact same thing going on for eternity. So CH3, H, 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 and on and on and on. And that is what an addition polymer is. So they're asking for the carbon-carbon-carbon bond angles. Well, first of all, if you were to split it up like that, you know that each of these carbons are going to be sp3 hybridized because you have 1, 2, 3, 4. So again, that is sp23. And sp23 means that it is sp3 hybridized, and that means it is tetrahedral. And a tetrahedral atom has 109.5 degree angles on all of its bonds, which means each of these carbon-carbon-carbon bonds will have a 109.5 degree angle, but again, you round, so it's 109. It's not B because, again, you only get 120 if it's sp2 hybridized, which means it is planar, and you'd get something like that. So it'd be a double bond and 2 single bonds. So that's not right. Half of them are 90 and half are 180. Again, that wouldn't make sense either because that would mean you need an octahedral structure, which is typically drawn out like this. So you have dashes and wedges and like that and like that. Typically you get those in ions, so like complex metal ions. And again, that's A-level chemistry, so you don't really need to know that. So that is gone. And then they're all 120. Again, that only makes sense if it is completely sp3 hybridized. So that is gone too. So yeah, that should be answer choice A. Question 25. An alcohol has the molecular formula C5H12O. Okay, so we know it's an alcohol, and we know that's the molecular formula. What forms a yellow precipitate with alkaline aqueous cyanide? Ooh, okay. So the first thing that comes to mind whenever you see this word yellow precipitate is triiodomethane. And what triiodomethane is, it is CHI3. And you also call it iodoform. But you don't really need to know that, but that's just another name for it. If you did paper 4, hopefully you knew that. And you get this if you have a methyl ketone, which is basically something that looks like that, you have something attached to a CH3 and then a CO. So yeah, there's that. Or you can also have a alcohol in position of that ketone. So like that. So we just need to find a molecule that has something like that. And you can either just, predict it. So you could go like, I don't know, let's say you have OH. Well, first of all, you have 2 carbons already. So you can just attach 3 more. So 1, 2, 3. And you'd be like, whoa, that is our C5H12O. But you'll see that there is no there's no pentan-2-ol anywhere, right? I mean, you have a pentan-3-ol right here. But pentan-3-ol, what pentan-3-ol looks like is 1, 2, 3, 4, 5, like that. So pentan-3-ol does not have this group right here, so that won't work. So we can eliminate that one. So again, it might just be better for you to just plug in the answer choices and just see which one has it. Yeah, let's just go from the top down then. Sorry for starting with the last one. 2,2-dimethylpropan-1-ol. Okay, so this was answer choice D. Answer choice A looks like this. So propan looks like that. It is just 3 carbons. 1-ol would mean there's an, oh my god. 1-ol would mean there's an OH right here. So OH, and it says 2,2, so then it's like that. This one does not have that group again, so it can't be A. If we look at B, 2-methylbutan-2-ol, that looks like, let's see, butan is that, 2-ol, so there's an OH here, that, and then it's also 2-methyl, so it's like that. Again, you don't really have that group right there, and although this right here might make it look confusing, you can't really split that off because, again, that is a tertiary alcohol. That is not really anything special. So you can't have like another group attached like that. It has to be a secondary alcohol like that. So it can't be answer choice B either. So that leaves us with answer choice C. And what that would look like is 3-methylbutan-2-ol. Okay, so butanol looks like that. Butan-2-ol would be the OH. Okay, that looks a bit promising. And 3-methyl would look like that. And that indeed has the group we're looking for, which is this right there, the CH3, which is right here, and then the COH, which is right there. So answer choice C is our answer for this question. Hopefully that made sense. And this is actually a really good one to know, so hopefully that's good for you if you know it. And starting on from here, by the way, there's a lot of organic chemistry. So if you don't know your organic chemistry, I think it's probably a good time to brush up on it, especially since paper 1, about 50% of it is organic. So anyways, moving on. Question 26. When compound X is heated under reflux, okay, with aqueous sodium hydroxide, 2 products are formed. So sodium ethanoate and hexan-1-ol. So sodium ethanoate, just think about it like this. Whenever you see the sodium and something O8, just think of it as this thing right here, and then add the oic acid. So ethanoic acid, that would look like this, right? So you have a double bond O and then an OH, but it's sodium ethanoate. So all you have to do is after getting that ethanoic acid, just take off the H and then pop on an Na. That's literally all it is. This is what you name sodium ethanoate. And that is an easy way to help you remember how to draw those out. And it also says you form hexan-1-ol, which is pretty straightforward. That's hexanol. Well, that's hexane. 1, 2, 3, 4, 5, 6, and then 1-ol. So that's what it looks like. And treating it with aqueous sodium hydroxide basically means you're hydrolyzing a bond. So if you look in the answer choices, all of these are esters. And if you hydrolyze it with sodium hydroxide, you basically split it along this bond right there, which is how you get the OH from this, and then how you get the ONA, which is from that. So basically what we're doing is, since we're splitting it like that, all you have to do is look at this right here and group them together. So what that'll form is you start out with this as normal, bunch the O's together, and basically kick out one OH and kick out an Na so that you're left with NaOH, because that's what we have, sodium hydroxide. Attach that O on there because it's still there, and then connect them. So let's see, 1, 2, 3, 4, 5, 6 carbons. So it would be 1, 2, 3, 4, 5, 6, like that. That way you have 1, 2, 3, 4, 5, 6 carbons like that. So this is the compound that you started with. This is our compound X, but they wrapped it around in a ring, as you guys can see. So all you have to do now is just count. So the first thing you should do is take a look at the answer choices that do not have this CH3CO. And if you look at it, this one, first of all, does not have that because that has a bunch of things attached to it like that. We don't have a CO and then a CH3, so that can't be right. Same case here, you don't have it, you have this bunch of stuff, but again, that's not a CH3. Meanwhile, these two do. So now comes the other part where we count the number of carbons at this part right here. And we already counted that there were 6 carbons because again, we had hexan 1-ol. So counting them up, this has 1, 2, 3, 4, 5, 6, 7 carbons. So that can't be right. And this one has 1, 2, 3, 4, 5, 6 carbons, and that is indeed correct. So answer choice D would be the correct option for this question. So yeah, that's all you have to do. Make sure you remember, first of all, what sodium X8 would be, and then just know that it's X-anoic acid, right? And then, of course, knowing how to combine them and knowing what hydrolysis is. So yeah, hopefully that helped if you didn't know that. Let's move on. Question 27. What is the major product of Z following the following reaction? Okay, so an excess of dry HBr. Why that's important is because if you have water, it actually will interrupt with the actual reaction. So you can't have water in there. It basically just means it's like pure HBr. So, and then you're warming it. You're gonna get a product that looks something like this. So let's just start out with this. Boom. Because basically what you're gonna do is you're gonna remove the alkene and you're gonna attach a Br either here or here. And the question now lies, which one is more stable and which one will it react with? So this is a mechanism question. So what you need to look at is, I'm gonna just look at one section. Let's take a look at what would happen if you have this as an intermediate or if you would have this as an intermediate. So the two differences between these two options. Option one is you have a primary cation. So what this primary carbon cation will do is it'll basically substitute with this first and then move on. Or option 2 is we use a tertiary carbon cation. And a tertiary carbon cation, if you guys don't know this, is much more stable than a primary carbon cation. So it'll actually go with this one. So option 2 is actually the better option, which means that bromine is going to substitute in at that position, like that. And the same case here, would you go with that one or would you go with that one? This one is more stable because it is the tertiary cation. So that would be our overall molecule. And I do believe that is answer choice B because, again, it attached at the position where you have a tertiary carbocation instead of where you'd have a primary one. Well, yeah, basically. So that is how you'd answer that one. Answer choice B. Oh, wait, whoa, sorry. The thing wouldn't be there. Option 1 would actually be, sorry, I answered that incorrectly. Option 1 would actually be here. The plus would be here. And that, either way, that's still a secondary cation. And a secondary carbocation is still less stable than a tertiary one, so it would still substitute at the option 2 position rather than the option 1. And again, same case here. Sorry for that misstep. It would have the option of substituting either, for this one here or here, sure. So again, that one's primary, that one's tertiary. Tertiary one's more stable, so it substitutes there. So yeah, that's why this option would be incorrect, and that's also why these answers really don't make sense, because that at that point you're just defying the laws of chemistry, and they'd be doing something pretty weird. But yeah, if you had to choose between option B and C, just remember, more stable with the higher number, so just go with that. All right, moving on. Structure of compound Q, how many chiral centers? Okay, well, this one's really not that hard. All you have to do is really count up the chiral centers. So the tip when doing this, some of you guys might have trouble doing that. All you have to do is take a look at where there is a position where there's 4 different groups. So whenever there's a hexagon, right, you might think, oh, that might not be a chiral center. Well, if you take a look at it, if you go around this way, it's going to be a different formula of carbon atoms than if you were to go this way, because then you'd have this first. And as you can see, this length right here is longer than the other length, which is this one right here. So that's actually a chiral center right there. So using that logic, we have one chiral center right here, we have another one right here because there's a hydrogen and then again, hexagon, hexagon, and right here you get a different hexagon, so chiral center. There's another one right here, again, same logic, you can go that way. There's another one here because you get a different group every time you go that way. It can't be this one because chiral centers can only exist where there's an sp3 hybridized carbon, so that doesn't work. This one works as well. This one would actually work too because, again, two different groups. You go that way, you get this, go that way, you get this other big stuff right here. But yeah, so using that logic again. 1, 2, 3, 4, 5, 6, and then our last one will be right here, 7. Because all these ones, that one's sp2 hybridized, so that one doesn't work. This one has the two same groups right here, CH3, and yeah, that's really all there is to it. So there are 7 total chiral centers. So 7 centers. I'm not a British person, so I don't spell it like that. But yeah, there are 7 chiral centers. So the answer choice right there is answer choice D. And I believe that is correct. All right. So hopefully that helps if you didn't know how to count chiral centers properly. Just essentially just look at it and take different paths. If you get a different path, if you follow it, then it's a chiral center. All right, question 29. All right, we have our last 2 questions for this video. Compound X has the infrared spectrum shown. Okay, and then we're asking the identity of compound X. Okay, so the first thing is you probably need a data booklet for this. So here, let's figure out where it is. It should be this one right here. So this is, I believe, page 14 on your data booklet. It is basically the characteristic infrared absorption frequencies. So I've actually kind of memorized a lot of these. So if you don't memorize them, that's still fine. The ones that you should know by heart after using this a lot of times is this zone right here. Just know that if you ever have a peak near 1700, that is most definitely a ketone bond or just a carbonyl bond in general. So if you have a COO, that is most definitely going to be a peak at 1700, and you can tell because it's really sharp, it's really narrow, and it's basically always near that range. So anything between this zone right here is going to be a carbonyl. Meanwhile, you also have this broad peak right here. And this broad peak really only appears when you have an alcohol. So it might not be the typical like broad peak that you might be used to that looks something like that, but it's still an alcohol peak. And this is actually an alcohol peak that's characteristic of a carboxylic acid. And you know that because carboxylic acids actually have this thing right here that is different from alcohol, which again is more smooth like that. So this is probably going to be some sort of carboxylic acid. So it's probably answer choice A. But let's just take a look at the other options to see why they're not the case. And again, by the way, you guys can see carboxylic acids have 2500 to 3000 in comparison to the other alcohols, which are, again, a bit more higher than that. But yeah, so 2500 to 3000, again, you can tell because that's like right here to right here, like that. All right, so we already know that it's probably ethanoic acid because we have carbonyl and an alcohol. It's not ethanol because ethanol looks like this, and it does not, oh my god, what happened to the pen there? Ethanol looks like, oh my god, here, ethanol looks like that. So there's no carbonyl bond, there's no double bond O, so this one can't be it. Ethyl ethanoate, so ethyl ethanoate looks something like this, so ethyl ethanoate will O like that, because again, ethyl is this right here, is 1, 2, O8, ethanoate, so ethane is right there, and this one is actually just an ester bond. So an ester bond would be from 1040 to 1300, and as you guys can see, there's not really any significant bond right there. So it's actually not going to be an ester because it's going to be just a strong peak. And as you guys can see here, there is not really a strong peak between there. I guess you could say that, but that's really more of a alkane bond. But yeah, moving on. Ethyl ethanoate, so we said that was out. Oh my god. And propanone looks like this, but again, there's no alcohol, so it can't be that one either. So we're left with answer choice A. And that is the correct answer. All right, last question. Which reaction produces an organic anion? Okay, so anion, you guys know, has a negative charge with a good yield. Okay, so let's just go through these real quick. Heating ethane nitrile. Okay, wait, I'm actually going to solve the questions down here. So heating ethane nitrile under reflux with dilute sodium hydroxide. So ethane nitrile looks like this. So you have the C2H5, and then you have the CN, like that. And then you're treating it with dilute sodium hydroxide. So what this will do is it'll actually form a carboxylic salt. So what this will do is it'll turn this into a carboxylic acid of sorts, but it'll actually substitute like that. And this is what you're going to get. And because you have a bunch of sodium hydroxide in there, this is actually going to be under basic conditions. So this will actually split up into ions because it is an acidic compound. So you're actually going to get O minus and Na plus in your solution. So we basically already know that we have our organic anion right here. So answer A is probably going to be it. But let's just take a look at the other choices just to confirm. Answer choice B. Heating ethane nitrile under reflux with dilute sulfuric acid. Okay, so this one will actually do a similar reaction, but it'll actually just form the actual carboxylic acid. So again, same case as last time, but there's not going to be an Na, and instead it'll just be OH. Now, this is under acidic conditions, so that OH won't split. So what ends up happening is you don't actually have an anion. It just remains in acid form. So what that means is you're actually not going to have a negative anion at all. So answer B is actually not correct because there's no anion. It's just carboxylic acid. It's just propanoic acid. So yeah, watch out for that. Answer C, heating ethane with sodium metal. Okay, so that just means you're heating this. That kind of looks weird, but C2H6 with sodium metal, which is Na. No reaction is actually going to occur for this one because there's really nothing for the sodium metal to react with. Sodium metal only really reacts with an alcohol group. So it would react with like this or this, but it won't react with any of these. So there's going to be no reaction for this one. So we can basically just rule out answer choice C, saying, well, that's not going to do anything. And then for answer choice D, heating ethanol under reflux with dilute sodium hydroxide. Okay, so ethanol looks like this. Sodium hydroxide is NaOH. Again, this won't do anything either, because what is the sodium hydroxide going to react with? This is just Na plus and OH minus. What is it going to react with the ethanol in? There's really nothing you can do. So again, answer choice D won't have a reaction either. So you're only really left between answer choice A and B, and the answer choice will be A because, again, because answer choice A is under basic conditions, it's actually going to ionize and deprotonate. So it's actually going to form O minus and Na plus in comparison to this one, which is under acidic conditions. So it won't actually form, it won't form this because it is in an acidic condition of a low pH. So answer choice A is your correct answer here. And I believe that is correct. Yep. All right. So that is our last question for this video. Next part, we will finish up all the questions. So questions 31 through 40. All right. It's a bit of a weird organization. And all these questions are going to be multiple correct. So each one will have 3 answer choices, and I'll have to show you one by one like I've been doing till now. So hopefully that'll be a bit faster. But that was all for this video. Hope you guys learned something new, and I will catch you guys next time. Have a good day, and see you guys later.